So, good evening, everyone. Welcome to week 3 of Analog Electronic Circuits live problem solving session. In today's session, we'll be going through the problems based on CS amplifier, CG amplifier, and CD. So, before starting with the problems, let's just discuss the basic concepts of these circuits. So, when we say CS, CG, CD configurations, what are the basic key points that we need to keep in mind while talking about these configurations? That is the first thing that comes to our mind, right? So when we say CS, what does this mean? Like, first of all, where do we give the input in CS and where do we get the output from the CS? If it is a common source amplifier,
Hello, ma'am.
yes,
Are you
yes.
sharing screen something?
Yes, I am sharing the screen. Is my screen
Yeah,
visible?
not visible for me. It's my problem or
So it's a iPad screen, like you can see me writing because my screen is visible to me. So
Yeah, it is visible. I can also see.
Visual ma'am.
okay.
yeah, there might be
Okay.
some network issue. So that what?
Yeah, I will rejoin. No problem.
Yeah. Okay. So when we talk about CS amplifier, where will we give the input? We'll give our input to gate, and output will be received at drain. Now, if we say CG amplifier, then the input is at, where do we give the input and output? And similarly, if it is a CD amplifier, where will you give the input and where will you get the output? See, CS is very common, everybody knows that. But what about CG and CD? Gate is common. See, CG in CG means common gate. So if common gate, then where will we give the input? Gate is common. I have already told you that there is only one input port, right? Last time when we were discussing the port diagram of a MOSFET, we said it has source, drain, and gate. This is your input port, and this is your output port. Or rather, I should say, this is your output port. So you can only give input through source and gate, and you can get only output from source and drain. So you can never get an output from gate, and you can never give an input from drain node in a MOSFET. This is given. So with this idea, now let's with this idea, let's move ahead and see, okay, when there is a common gate terminal, that means your gate is common. Now you have two terminals left, source and drain. So where will you give your input?
Source.
Source. You'll give your input at source and get your output at drain. Now when there is a CD configuration, which is common drain configuration, the input will be given to
Gate.
gate and output will be taken from source. So this is something which is very basic and we have to keep it in our mind. Other than that, if I talk about the basic features that we have in these particular configurations, so if I talk about gain, so in CS amplifier, it has high gain. Okay. In CG, it also has high gain, similar to that of CS amplifier. Now, when we talk about CD amplifier, the gain is low. And when I say low, it means less than 1. This is something that we need to keep in mind. Other than that, Other than that, so if the gains are similar, then what makes common source and common gate different, right? That might be the question. So see, when you observe very carefully, you are giving input at gate in common source. So the input impedance, if I talk about the input impedance, it is very high in case of common source. Whereas when you are looking at common gate, your input impedance is at source. So it is low. So we should always keep in mind that when we design an amplifier, especially a voltage amplifier, we want our input impedance to be high. Okay. Now what about if it is a current amplifier then? If I say that for a voltage amplifier, my input impedance should be very high. So if it is a current amplifier, my what should be the characteristics of my input impedance?
Low.
Yes, low. So at that point of time, you can use a CG configuration, right? So depending on our needs, we'll use whether we are going for a CS amplifier, CG amplifier, and what about CD? Like when there is a gain less than one, where will you use this amplifier? It is not even amplifying, right? So what is the use of this amplifier?
Which is CD, this buffer, maybe buffer driver.
Yes, well said. So it is buffer. Buffer, or you can say these are used for impedance matching.
Impedance matching, correct.
Impedance matching, yes. And if you observe very carefully, in both the configurations of CS and CG, the output node is drain. And when we talk about the impedances, the range of impedances or the impedance flow is like RG, that is gate impedance is highest compared to RD, then RS. This is how the impedances look like in a MOSFET. So if you observe very carefully in CD, your output impedance is at source. So your output is from source. So when you see your output impedance, it is actually low. And when we are using a voltage amplifier, like voltage to voltage amplifier, your output is a voltage, your output impedance of amplifier should always be low so that all of your voltage transfers to your load. That is the idea. So depending on which type of amplifier you want, whether it is a current to current, current to like voltage to current, voltage to voltage, current to current, current to voltage, depending on those, your characteristics of input and output, mostly impedances changes depending on loading effect. Have you heard of loading effect? What is loading effect? Okay,
Uh,
anyone?
Input input adjusts as per as the load changes.
Loading effect. Okay, so let me explain it to you with an example. Let's say I have a source. Okay, it is a voltage source. It has some input impedance RS, right?
Mm.
This is your complete V source, and you have, let's say, a load connected to it. Now, I have my RS, which is fixed for a source. When a source is designed, its RS or input impedance is always fixed. So let's say my RS is 1 kilo ohm. Okay, and now you have your RL load which is changing. So let's say to that particular source you have connected a bulb, or you have connected a tube light, or you have connected a speaker, you have connected a fan. All of these have different load values, right? They have different impedances, they have different loads, and depending on these loads, actual voltage that appears across the load changes. Now for example, let's say your RL is 10 ohms or 50 ohms. Mostly your speakers and all have 50 ohm resistance. So if your load is a 50 ohm resistor, and your RS is 1 kilo ohm, considering your source is of 5 volts, what is the voltage that you will actually see across your load in this particular case? So, how do we calculate? By voltage divider rule, right? These two are in series, which is like around, which is around 0.25 volts, right? Now, let's say if my RL is 1 kilo ohm, then my VRL will be how much? It will be 2.5
Excuse
volts.
me, ma'am.
Yes.
That is what you have written is 1000, but that is 1050.
Yeah, 1050. I have approximated it to 1000
Okay,
because 1000 and 1050 will not make much of a difference. So that's why I approximated it. So you can see approximation
fine,
sign here,
fine,
right?
fine, ma'am.
Yeah. Now let's say if my RL is 1 mega ohm, what do you think my VRL will be? Or let's make it 10 mega ohm. What do you think my VRL will be? It will be almost close to 5 volts, right? Very close to 5 volts. Or let's say if I make it even like a huge value, 500 mega ohms, then so definitely your VRL will be close to 5 volts. So this is what is known as loading effect. So this comes because of the different resistances and voltage sharing between the resistances. So when you are designing a circuit, what you want to take maximum out of your source, right? If you are connecting a circuit, or let's say if you have a speaker and you want to use that speaker with a voltage source, so you want the maximum voltage out of that voltage source to drop across your speaker, rather it going waste into the internal resistance of the speaker, right? That is the idea. So everywhere we try to look into these resistances, and based on this, what we call as impedance matching is done. That means, for example, if I know that my RS is 1 kilo ohm, then I would make sure that my RL needs to be more than at least 1 mega ohm, so that my maximum voltage from the source can be drawn across my RL rather than RS. So that is what is called impedance matching. That is purely done to actually extract maximum out of your sources. Or even if, let's say, you have an amplifier, you have an amplifier with its input resistance, and then you connect a load, or amplifier with output resistance and you connect a load. So what you want the amplifier's output to be like, you want its output to appear across the load rather than being dropped across the output resistance, right? So when you hear the terms like loading effect, impedance matching, so what we are concerned about is this particular thing, that we should make sure that we can get maximum from our, let's say, source or from our circuit in our output, rather than it being consumed by the circuit or the source itself. So that is the idea behind a loading effect or impedance matching or everywhere. So that's why whenever we talk about circuits or sources, we always talk about the impedances, because impedances play a very key role. Now, if you look at this particular example of loading effect, here if we would have neglected the impedances, let's say RS would have been neglected, we would not have considered. So what we would expect that in every particular case, we want, like, we know that the source is of 5 volts. So across our output or load, we should always get 5 volts, right? But we are not getting the 5 volts. Why? That is because of this RS. So it is very important to understand the impedance behavior of your circuits and their elements too. So that's why whenever you analyze circuits, it is necessary to analyze their impedances too. That's why we also talk about uh, gate, drain, source impedances, as well as if there is a voltage source, then the impedance of that voltage source. If there is a current source, impedance of that current source. So all these is done for that particular reason. Even in terms of diode, like last time you might remember that there was a piecewise linear model. There we drew a diode with cut-in voltage, also with the internal resistance, right? So that is the resistor, like that is the resistance that appears across the diode. So every element, even a single piece of wire, has its resistance and its impedance. So each and everything around this world, all the components, everything, even human body has a lot of resistance. Like we have some hundreds of mega ohms resistance. That's why. And we are always grounded, so we don't get shocks. And since it is a high resistance path, so yeah, so that's why human body also has resistance. So each and everything all around us has resistance and impedance, and it is very important to understand the behavior of that resistance. So that's why that's what I wanted to highlight. And these impedances can be analyzed, and this come into picture when we talk about loading effect, impedance matching. In all these terms, we consider these impedances. Now, with this, let's move on to our first problem, which is, yeah, okay, which is this first circuit. So, in this circuit below, it is mentioned that this is used for to work out the DC operating point of the circuit, and it is a N-type MOSFET. It is already given that it is an N-type MOSFET with a VT of zero point 0.5 volts. The device operates according to ID equal to K VGS minus VT whole square. So, what does this equation, current equation, tells us about the MOSFET? Looking at this equation, what is the behavior of the MOSFET? What does this current equation tells us about the MOSFET?
Saturation.
Saturation.
Yes, it
Saturation.
tells that the MOSFET is already in saturation. Now R1 and R2 are already given for 4 mega ohms and 1 mega ohm. With this, what should be the RS such that the current ID through the device is 119? Okay, so it's already mentioned that ID is 119 microamperes. Give your answer in kilo ohms. Assume RD is such that the device is in saturation. Okay, so in this particular question, you have to find RS. We have to consider RD such that the device is in saturation, and we have to find RS. So, how would we find the RS? Now, first things first, what is this? This is VG. Here we will have VS, and this is VD. With this information, first thing that we need to know in this ID, that is current equation, is VG and VS. So how to find VG? By voltage division rule, right? So we can find simply VG as 1, sorry, 5, 1 upon 1 plus 4. So VG is 1 volts. How come VG is 5 volts? How can you say that VG is 5 volts? Yeah, it's a voltage divider, right? So we have to apply the voltage division. Yes, 1 volt. Now, what is Vs? So how do we write Vs? It is ID Rs. ID is known, but Vs and Rs are unknown. And also, what about VD? How do we write VD? So VD can be written as VDD minus IDRD, right? At this point. So these IDs are same. All the ID that is flowing in this branch will be same ID, that is 119 microamperes. So here you know ID, that is 119 microamperes, is equal to K is already given 4.12 millisiemens per volt into Vg is 1 minus Vs is VDD 5 minus 119 microamperes into Rs minus Vt was zero point 0.5 whole square. Now here you have a single equation with one variable Rs. So we can find Rs, right? Simply. Can we find Rs? Yes, come on.
Yes.
We can find Rs out of here, right? Or what else can be done? 119 microamperes is 4.12 VGS minus VT whole square. So we can simply solve it first and we can find like VGS minus VT is root under 119 microamperes by 4.12, which is 0.17 volts. And from here we can simply find 1 minus wait VG. Oh, this is not VD, right? So why 5 minus? This is VS. So here it will be 1 minus IS RS IDRS. So 1 minus 119 microamperes into RS minus zero point 0.5 is 0.17 volts. So which gives us the RS as 2.77 kilo ohms. So this is what the value of RS that we will get. Okay. Now here at the first glance, we would have thought that okay, RD is not given, RS is not given. How will we going? How are we going to solve it? Right? There are two variables. But see, if you see here in the like very first equation, there only we used one variable, which was RS. We never used RD. So sometimes we should not panic with what are given and what are not given. Slowly, if we start solving, we can reach to the end. Okay? Yeah. Moving on to the next problem. In
Ma'am, I
this,
have a doubt.
yeah, please go ahead.
Ma'am, when we have to use RD to find the answer, then
Okay.
what value should we assume it, ma'am?
So see,
If
that's a tricky part. Now here, if you want to say solve for RD, then RD cannot be solved. Like you cannot take a random value and solve it because the value of RD will definitely affect your currents. So the better way is always try to use as like less number of parameters as possible, especially unknown parameters. So always we should find the equations which have lowest unknown parameters for solving rather than going for an equation which consists of many unknowns. We should go for the equations which have lesser number of unknowns to solve always. That is the key rule.
okay,
And
ma'am.
yeah, because there is a equation when you go by, let's say, a KVL from VDD to your ground, there you'll find like VDD equal to what? IDRD plus VD plus IDRS, right? Now, in this particular equation, you can go by this equation as well. But what is the problem here? Here, there is, first of all, it is a single equation with two variables. And
Yes.
rather than when we are solving this particular equation, so here we have a single equation with one variable. So it is easier to solve a single equation with one variable than to solve a single equation with two variables. Now what you can do, since you have found the value of RS, you can substitute it here and go ahead and solve. But starting with this particular equation is a tedious job and better avoid it. So yeah, always start with equations with less number of unknowns first. So that is the key rule.
Okay, ma'am. Thank you.
Yeah, okay. So let's move ahead to the next problem. So in this problem, you have to find, so for the same given circuit, we have to find the GM, right? And give answers in microsiemens. So what is the value of GM? What is the expression for GM in a MOSFET? We did it last time, right?
Two under
Two
root
idea.
KN RD.
Sorry. Yes, what was it?
2 under root KN into ID.
2 under root
KN into ID.
K into ID.
हाँ.
This was it. Okay, so here you have like 2 into, you know the K was how much? 4.12 millisiemens per volt. ID is 119 microamperes, right? So what will be the GM that you are getting? What is the value of GM?
1400.4.
Sorry,
Option C.
1400.4.
हाँ,
Option
1400.
C. Yes,
Hmm.
1400.4. What will be the unit?
Microsiemens.
Sure, pakka microsiemen.
Yeah. Yeah.
Okay. See, be very, very careful with the units, okay? Because units can take your question from up to down. So it's like it can create havocs if you lose units. So be very careful with the units. Yeah, let's move on to the next problem. So in this problem, for the same circuit, now see, okay. So in this problem, it says your ID is K VGS minus VT whole square 1 plus lambda VDS, right? So first of all, looking at this equation, what does this equation tells you about the transistor? What is the mode of operation of your transistor?
Saturation.
Saturation? Okay. Yeah, I do agree. It is in saturation. But what does this mean? Like, what is this extra term?
Channel length
Channel.
modulation.
Sorry? Yeah, it is channel length modulation. So earlier, last time also, there was a mention of lambda term, right? And it was mentioned in last week's problems that lambda is 0. So what will happen if lambda is not equal to 0? So when lambda is not equal to 0, it introduces this non-linearity, or basically the second order effect that we call an MOSFET. And it is channel length modulation. So ideally, how do we want our output characteristics of a MOSFET to look like? We want it to rise linearly and then saturate completely, right? So this is the ideal behavior that we want out of our MOSFET, and this is the behavior when lambda is 0. That means there is no change in current with VDS. So independence from VDS. That is when we call it as a ideal current source too. Now, in practicality, what happens is actually your current does not saturate, rather, it sees a slight slope and which changes with VDS. So, there appears a dependence of VDS on your current, and that is due to the channel length modulation effect. And this factor of channel length modulation is defined by lambda, and in these cases your lambda is not equal to 0. Clear? But still your transistor is in saturation. So this channel length, first of all, the channel length modulation effect comes into picture after your transistor is in saturation. Okay, so only your current for saturation changes with this extra term of 1 plus lambda VDS. Clear? Any doubts? Yes, any doubts?
Ma'am, can you repeat?
So, which part do you want me to repeat? Whole of it or like from where?
Ma'am, about the deviation of the graph.
Okay, deviation of the graph. Right. So, I don't want to go too much into the physics of the transistor, but ideally, how we want our transistor characteristics to look like is lambda equal to 0 form, right? Where we say that in saturation, your current does not depend on your VDS, that is your output voltage. That was the basic idea. Now, what happens in practicality when nowadays we say that the transistors are shrinking, right? So with the shrinking transistors there is a new problem that is basically encountered. We call it a second order effect, and it is named as channel length modulation. So because of which what happens, your saturation current, which was independent of VDS, that is output voltage earlier in larger transistors, now that current becomes like uh, start seeing a dependence of VDS or output on itself. So that current is now, it is not independent of VDS, rather it slightly increases with increase in VDS. So that's why you see this dotted line type of curve. And because of this, your current is actually not saturated, or it's not a constant value. So it's not an ideal current source anymore. Okay, it is a practical current source, and there is a slope. This slope is known as GD, or we can call it like 1 by R naught, which shows you the output impedance of your MOSFET. And this nonlinearity, or this slope, is also denoted in terms of lambda. Okay, and this lambda is now not equal to 0. So earlier it was equal to 0, right? When we said it is a ideal MOSFET. Now the lambda is not equal to 0. And this effect is known as channel length modulation. Is it clear?
Yes, ma'am. Thank you.
Okay. So with this information, now what we have to find out is what is the value of R naught. So R naught, how do we find R naught? Sorry, is there any question? You can please unmute and ask. It would be easier. Yeah. Okay, so what is the problem that we have to find R naught? How do we find R naught? It is dV naught by di naught, right? What is dV naught and what is di naught? So d, or if I say like dV out by di out. So here V out is VDS, I out is ID. So when we say R naught, it is dVDS by dids. Now we know that ID is kVGS minus VT whole square 1 plus lambda VDS. So let's say if I take DID by dVDS, then what will I get? Whole square into lambda, right? So if you observe this very carefully, what is this? This is your ID sat, right? kVGS minus VT whole square is your ID sat, right? And into lambda. So now when I want dVDS by dID, it is simply 1 upon lambda ID sat, which is R naught, which we call it as output resistance. Now we know ID sat from earlier equation. We know our lambda, so we'll simply substitute and we'll get the values. 0.014, 0.01 volt per volt. Yes, it is 0.0 volt per volt, 0.04 per volt into 119 microamperes. Yes. So what is the value of R naught that you are getting after solving these two? So the answer that you should get is 600.24 kiloohms. Is this clear how we got the expression for R naught? Any doubts? Okay, hope this is clear. I guess there was some question.
Excuse me, actually, ma'am, I have one question
Yeah,
regarding the
please.
previous one.
Yeah, please go ahead.
The regarding the previous which you solved, right?
Previous
Um,
problem. Yeah, okay.
yes, yes, yeah.
Yeah, yeah.
So in this problem, the problem which we have in our assignment, so I'm doing the same way. Uh, uh, but in the options, it is not matching. It is exactly kind of my value is half of the value which is mentioned in the option. So
Okay.
is
Yeah.
there any
So
discrepancy? Maybe because in this problem the k is different.
yeah, that might be the problem. Sometimes, okay, I'll let you know what.
Yeah,
So it also depends on how you represent your expression for ID. Sometimes we say, okay, ID is k VGS minus VT whole square. Sometimes what people say it is k by 2
yeah,
VGS minus VT whole square. In real, so what is the basic value is mu n Cox W by 2L VGS minus VT whole square. So what happens? Sometimes people report K as mu n Cox W by 2L, whereas sometimes people do report it as mu n Cox W by L. So in these two cases, so there is a discrepancy of two, and sometimes it does appear. So that's why in many of the problems you might have already seen that they have given you the expressions, right? And this particular question also, the first one that we solved, it was already mentioned like what you should consider your ID to be, which was
yes,
K,
yes, yeah.
which already
So
considers the
yeah.
division of 2. And in the next question that we are going to take, so this was the question that we have taken right just now.
Mhm.
Here also they have already mentioned that it is K. So where it has considered the effect of K by 2 has already been considered. So that is where the discrepancy comes from. So
Okay,
just try
because
to check.
while I mean when I am doing so I am taking k not k by 2
Okay.
and doing the derivative of that one which is giving me 2k VGS minus VT, um, and while solving for that, right, it is giving me around 935 micron as the GM.
Yeah, because
Which,
when it is 2k Vg by Vg minus Vt, so it will be like
because if I'll consider k by 2, right, then it will be again it will be 935 by 2 it will come, which is again which will be give me wrong answer.
yeah. So you have to be careful with what is the concentration of k in that particular question, whether they are considering like division of two or not. That is something you need to look into. Otherwise,
Yeah, in question it is mentioned we have to consider k because id is k multiplied by vgs minus vt whole square. But
okay.
while using that equation, right, it is giving me 935, which is not matching uh, the options. So what I felt is it any discrepancy in the options or maybe some typo or something?
Mm, that then you have to invoke an the forum. Like, and if
Okay.
you ask that particular problem in the forum regarding the options, whether they are correct or not, they might help. Because ultimately, your questions will be graded depending on what is the value uh, that is mentioned in the option and what is the correct answer out of those in the options. So, if there
Yeah.
is any discrepancy in the options, then that need
Mhm.
to be addressed in the forum. So, the moment you ask them in the forum, they'll reply and get back to you.
Okay,
Yeah.
okay. You mean we have where is the
You
forum?
do have the forum, right? NPTEL forum where you can post your problems and everything. NPTEL forum where you can ask your doubts and all.
Yeah, we have one option which is called ask a question.
Yeah. There you
Oh,
can
you mean
ask
so
your
there you can.
questions, and there TAs will reply. So we are not from the formation, like we don't
Okay,
form questions. We are not from the problem formation department.
okay.
So they might actually look into it and correct it from their end. Yeah.
Okay, sure, sure. Yeah.
Yeah.
Because what I feel, the question which you are solving,
Hmm.
which is giving us 1400 micronamps, right?
Yeah.
Micron, that GM. Uh, the same option it is mentioning in our assignment also, but their ID and K is different value.
So K and ID, if they are different, then you will get a different GM. That is as
Yes,
simple
yes,
as
yeah.
that,
But
right?
yes, but options are same, which is in your option, right? Exactly same. It is given in our assignment. So that is why I just suspected maybe there is something is missing.
There is some discrepancy that you mean.
Yeah, yeah, yes. And same it is happening in the question 3 also, which is our R naught, which we have to find.
Hmm.
Uh, but that is like close to, we are getting around some 610 or something. Uh,
Okay. So
but
you
I'm not
mean to
sure if
say these
someone can
questions
comment.
are same from your assignment questions? Is that what you are trying to say?
The options are same, which is showing, which you are showing, right? The options are same, but the K and ID value is different in our assignment. So that means
So
which will
if
give
the
us different GM.
it will definitely give you a different answer.
Yes,
Yeah.
but in the options that is not present. It is
So
same, exactly same. Yeah.
option set might be same, but your answer will be different, right? Here you are getting, let's say, 1400. In your
Mhm.
question, the answer can be 1260. That is
Yes, yes, yeah,
possible,
yeah.
right? That
Yes,
is
but in
definitely
option,
possible.
but in option that is not present. Option is exactly same as it is in your, right? Uh,
No, see, that's what I'm saying. Here you have four options. For this
okay,
particular
okay, okay.
question, you
Yeah,
will
I
have one particular answer. For your
yeah,
particular question, you will have another particular answer, which will be particular to that question, right? How does
yeah,
that matter if
okay.
the options are same?
Okay,
Anyways,
yeah,
out of
I got
four,
you. Yes,
one will be right, right?
yes, yes, yeah.
Yeah. Okay.
The answer that we get from this method is not matching to any of the options given.
Oh,
Mm,
so if that is the concern, then you have to go for forum. If the options if the options which are given and the answer that you are getting are not matching, then you have to consult the forum. Yes, that would be needed.
okay, sure.
Yeah. So you have to consult to the forum because that might be a problem with the options, like setting of options. So you can consult the people in forum. They will definitely respond.
Yeah, okay, sure. Thank you.
Yeah. Okay. So you're ready? Yeah. Okay. So third problem is clear to everyone, right? So uh, hope that this is clear to everyone. Moving on to the fourth problem. So in this problem, the value of RD needs to be chosen such that the device is in saturation, and also the drain can swing up and down around the operating point, and throughout the swing the device is on and in saturation. Assume that the voltage at the drain will change sinusoidally. Also assume that while the voltage at the drain is changing, the voltages at the source and at the gate are constant and not changing at all. What is the RD such that the amplitude of sinusoid swing is maximum? Give your answer in kilo ohms. And you will need to use two conditions for the upper limit on the voltage of drain, and use the fact that the current through the MOSFET has to be 0 or more. For the lower limit on the voltage at drain should be like VD is greater than equal to VGS minus VT. So we have to consider the same circuit. So let's quickly. Oh wait, here. Okay, here. The circuit is not mentioned, but yeah, okay. Anyways, we can consider the same circuit or any circuit in general. So what it says is, let's say if this is your transistor, this is your drain node. Here you have your gate. This is your VDD. And if you have, let's say, ground, a basic circuit. So you have to find this maximum swing which you can attain here, and the minimum. So maximum swing means this span, which is maximum and minimum. So that your transistor is always in saturation. And keeping this in mind, you have to find this RD. And also it was mentioned that VG and VS are constant, not changing. So when it says that VG and VS are constant, not changing, that means you don't have a RS over here. Okay? Since you don't have a RS over here, it is directly grounded. So it fixes your VS to ground, and your VG is some constant value which you can get either from a voltage divider or simply applying a voltage. Now with this, you have to solve the swing. So let's say, how do you find your swing? So for example, if your output is biased, drain is biased at X, so this DC level is at X. So what can be the maximum value that your drain node can attain, and what is the minimum value that your drain node can attain? Depending on that, this difference will give you the swing. And also keeping in mind that these should not truncate your outputs, or basically your sinusoid should be sustained. So you should not see any harmonics or any disturbances. So your sinusoid should be sustained. So in both the sides, wherever your sinusoid is sustained, so this particular from top to bottom, whatever the uh, voltage that you get, you call it as swing. So that is the idea.
Ma'am, why RS is not there?
RS is not there because here it is mentioned that assume your voltages at source and gate are constant, right? It is already mentioned that voltages at your source and gate are constant. So at gate, let's say it is constant, but for source, if there was a RS, then what would happen is according to your ID. So here, the change in like changing node VD actually will change your voltage at node VS also, right? Because the current is also changing.
Yes, ma'am.
But here it is mentioned that consider that Vs is constant. So how would you consider that Vs is constant unless it is connected to ground, so which is a fixed voltage ground Vs. So that's why we are considering that there is no Rs and it's only Vs, right?
Okay, ma'am.
So now first things first, we have to consider that our transistor is always in saturation. So what is the condition for saturation? VDS should be greater than equal to VGS minus VT, right? So VD should be greater than equal to VG minus VT. Source, we have cancelled the source from both the sides. So here your your VG is here your VG was 1 volts, right, earlier. The same VG, let's say 1 volt, and your VT is 0.5 volts. Then what is your VD? VD should be greater than equal to 1 minus 0.5. So VD should be greater than equal to 0.5 volts. Yes. So this is one condition. Now if your VD should be greater than equal to zero point 0.5 volt, so till what point your VD can reach? Your VDD is 5 volts. So your span for VD is like VDD minus zero point 0.5 volts. So your VD can attain from zero point 0.5 volts all the way to 5 volts. That is what appears from this particular condition, right? So VD can have a span of 4.5 volts. That comes out from this particular condition, right? So if VD is like 4.5 volts, so what can be the maximum amplitude that you can get? So it's like your VD can go from zero point 0.5 volts to 5 volts. So this is 4.5. The maximum sine wave that you can fit here will have an amplitude of how much? 4.5 by 2, that is 2.75, right? So, oh, sorry, 2.25. So this amplitude will be 2.25 and this particular point will be 2.75.
Ma'am,
So this, yes,
how did we get that VD greater than or equals to VG minus VT, ma'am?
this is the basic condition for saturation, right? Of a transistor.
That is VDS, no, no, VDS greater than VDS.
Yeah, but it is VD minus VS should be greater than equal to VG minus VS minus VT. We have like removed VS from both the sides, right?
Okay, okay, ma'am. Thank
So
you.
that's how we get it.
And how is this, ma'am? VDD minus 0.5.
VDD?
Minus 0.5.
So VDD is 5 volts. Here you have got that your VDD can be anything above zero point 0.5 volts, right? So anything above zero point 0.5 volts till what voltage? Till your VDD, you cannot go beyond VDD, right?
Okay, yes, ma'am.
So till what point you can have your VDD or VD? You can have your VD till 4.5 volts span, which is from 5 volts to zero point 0.5 volts.
Yes, ma'am.
And the sorry, the biggest sine wave that can be fitted in that particular 4.5 volt span is of 2.25 volts amplitude, which can be like the DC voltage will be at 2.75 volts, right?
Thank you.
Yeah. So now to get a VD of 2.75, what will be your corresponding RD? So VD is what? VDD minus IDRD, right? ID was already known that it was 119 microamps. Even here, if we would have like not considered Vs to be constant and we have considered Rs, some Rs, then too we can go on and solve like this because ultimately we are cancelling our Vs here, right? Both the Vs are being cancelled. So if we don't consider that our Vs is constant, still it is fine because the value of Vs is not coming into picture in our calculations. So yeah, now we do know ID, we know VDD, we know VD, so we simply find RD. RD is 5 minus 2.75 by 119 microamps. So what is the value of RD that we are getting? It is 18.9 kilo ohms, right?
Ma'am, can you clarify that equation VDD minus 0.5 volts is equals to VD, that one?
VDD minus
I'm from,
0. Point, this one?
yes, ma'am.
Okay. So in this particular equation, what are we doing? See, from this equation you have got that your VD can be any value greater than zero point 0.5 to keep your transistor in saturation. Clear? Is this clear?
Yes, ma'am.
Now, when you can have any value beyond zero point 0.5, so how high can you go with your VD?
5.
Until 5, right?
Yes, ma'am.
So from 0.5 to 5, what is the span that you get? It is VDD minus zero point 0.5, right? 4.5 volts.
Yes, ma'am.
And in that particular span, what is the biggest sine wave that you can fit? It is with the amplitude of 2.25, which will be like with the DC value of 2.75, right?
Yes,
Yeah. So this is how we have solved. Any doubts?
ma'am.
Ma'am,
Yes.
yeah, actually I have one question. So
Yeah.
ma'am, when I'm going to design this circuit and
Hmm.
I'm doing in 130 nanometer,
Okay.
so my this positive cycle is not going up to 1.3 because I'm keeping VDD equal to 1.3 volt. So there is some distortion.
Mm-hmm.
Yeah, ma'am. So actually there the gain is around 2.25, so it is not going up to 2.25. That much amplitude I'm not getting.
Yeah, yeah. So, see, this is something which is very theoretical. Practically, you won't get the swing as mentioned of 4.5 because you cannot. So, to make your this VD to go to 5 volts, you have to actually, if you observe very carefully, ID should be 0. Can you
Yes,
see that?
yes, ma'am.
So, is it practically possible that your ID is like 0 and still your transistor is in saturation and you are getting your VD? Is it possible?
No.
No, right?
And ma'am,
So,
one more question.
yeah.
So that middle point we are keeping. So for
Hmm.
getting the highest gain, we have to keep it in mid VDD and between the VGS minus
Highest
VGS.
swing, not gain. Highest swing.
So
Highest
okay.
swing, that means your positive and negative cycle both will be, first of all, equal and there won't be any distortion. So, that is
And
the idea.
ma'am, while doing the biasing,
Hmm.
so we have to keep VG in such a way that DC voltage.
Hmm.
So my MOSFET will remain in the saturation region. But if we are not able to, there is a one voltage that VG at which we will get a high gain. So if we shifted from that a bit, there will be a large
No, no.
variability in
See.
ID.
I'll tell you what. You can get very high gain, but your transistor may not be in saturation. And I'll tell you where. When you are in subthreshold mode or subthreshold region, you will get very high gain. Like the gain is really like it's too high. But you cannot have your transistors or you cannot have your amplifiers designed in a subthreshold region. Why? Because subthreshold region is not stable. It is metastable. So any moment it can switch between your like on and off. So that's why there is a chance that your transistor is not in saturation, but still you might get very high gain. But that is not advisable. Always your transistor first needs to be in saturation, and keeping that in saturation, now your task is to get the maximum gain out of it. That is your task. But your transistor should always be in saturation. So that is the idea.
So, ma'am, what is the best way to get the, I mean, get the best gain? What parameters should be vary?
So, in very basic terms, when you have, let's say, CS amplifier, what is the gain that you get? It is simply GM into RD, right?
Yes, ma'am.
So you can manipulate and see like how can you increase your GM or how can you like increase your RD. So whether increasing your RD increases GM, are they related or not? So you have to look into all those things and you have to come up with the optimal value.
So just I
And
have to.
for a single stage, it is like around 60 dBs or so that you can get practically out of a single stage CS amplifier. Not even 60, like, yeah, close to 60. I'm talking in 180 nanometer technology where I have worked upon, so I'm not very sure in your technology node, but yeah, in our technology node, the maximum that we could attain out of a uh, single state CS is 60 dBs. Yeah,
Thank you.
yeah, okay. So, any other doubts? Any
Ma'am, can you
doubts?
scroll up to the question, ma'am?
Sorry.
Um, uh, Ma'am, in that question, can you scroll up a bit?
This particular question? Yeah.
Yes, ma'am. Ma'am, what does the lower limit on the voltage at drain mean, ma'am? There, the last line.
Yeah, yeah. See, so here, as somebody was saying, right, that they were not getting the maximum swing till 5 volts because there, when you have like VD at 5 volts, that means your ID will be zero. But that ID is not possible to have a ID of zero and still your transistor to be in saturation. But why we are using that in the problem? Because if you read your question very carefully, it says that use the fact that the current through the MOSFET device has to be zero or more. So we have to consider the current zero condition as well as the highest current that we can get. And
So,
for lower limit, it says that your voltage at drain should be VDA is greater than VGS minus VT. Because this tells you the lower limit of your drain voltage, like the minimum drain voltage that you need to have your transistor in saturation. So
ma'am,
that's
so
why this
lower
is the
limit
lowest.
means 0.5 volts in this question.
Yes, yes.
Okay,
0.5 volts. So you can have your drain voltage from 0.5 volts all the way till 5 volts. So
fine.
that is what it was meant by these particular lines. And that's
Okay.
why we have used our swing also from 0.5 to all the way till 5 volts. Okay?
Yes, ma'am. Thank you.
Okay. Any other questions? Okay, let's move on to the next problem. In this particular problem, so we have like RA is the input voltage source resistance of 20 kilo ohms. RL is again 20 kilo ohms. R1 and R2 are still the same, that is 1 and 4 mega ohms, right? R1 is 4, R2 is 1. R1 is 4 mega ohms, R2 is 1 mega ohms. R is RD. Okay. Now, what is the voltage gain of this circuit? Now, first of all, how do we find the voltage gain?
Small signal model.
With the small signal model. So when we say gain, that is for small signal. So when we say small signal model, that means AC analysis. What will be the speciality of AC analysis in this particular circuit?
All DC components short circuit.
All
DC components short circuit.
all DC components short circuit. Okay, so let me put this to AC ground. What else?
Capacitors.
Capacitor short circuit.
Capacitors short
Mhm.
circuit. Yes, capacitors short circuit. So how does your circuit actually look like after this? Your circuit would look like somewhat this RA, R1, R2. This is how the circuit actually looks like with V out over here and V in over here. And what we have to find is gain. So what is gain? It is V out by V in, right? So how do we find V out by V in? Yes. How to find V out by V in?
Replace the NMOS with the small signal
KVL.
model.
Small signal model, we can simply replace it. So instead of our NMOS, what we will have is simply plus minus VGS ground RD. Is there any mention of R naught? Since there is no mention of R naught, let's consider that R naught is 0. There is no R naught, and we can simply, yeah. Or so here is a thing, like if we are going for the model, current model with lambda not equal to 0, then we have to consider R naught. If we are going with the current model that lambda is equal to 0, then we don't have to consider R naught. Is this clear? So there will be a slight change that is only in terms of your R naught. So here we will have GM, GMVGS. Now here, whether the R naught will come into picture or not depends on the current, like what is the current concentration that we have, whether it is like lambda equal to 0 or non-zero. Okay, and with that you will have your RD parallel to RL. Here it is V naught, and here we have R1 parallel R2 in series RA with V in. Okay. Now, first of all, what is the VGS that we will get? First of all, we need to find the VGS, right? Yes, what
The
is the VGS?
voltage division from
Using the voltage division rule, we will get it as V in into R1 parallel R2 by R1 parallel R2 plus RA. So this is how we will get our VGS. We do know our GM, right? We have calculated earlier GM was how much? 1400.4 millisiemen per volt. So this is the GM that we already know. So the GM into VGS is known. So what will be the V out? So V out is what will be the V out?
the KCL across the output voltage, the current leaving from the output node.
Yeah, current leaving from the output node into the voltage. So if we want to write it, we can write it as, so let's write a what do you say, KCL at V out. If we have a KCL at V out, then it will be V out upon RD parallel RL plus V out upon R naught plus GM VGS is equal to 0. So V out 1 by RD parallel RL plus 1 by R naught is equal to minus GM VGS. So V out is equal to minus GM VGS by R naught plus RD parallel R into R naught into RD parallel RL. Right here, in place of VGS, we have to simply substitute this. So it will be in terms of V in. Then we'll get V out by V in. Right? So, yeah, if I write it down here, so V out by V in is minus GM VGS R naught, oh sorry, GM, it is GM R naught RD parallel RL into, what is this, R1 parallel R2 divided by R1 parallel R2 plus RA into R naught plus RD parallel RL. So this is the expression that we'll get. And yeah, so after solving this, the gain that we will actually get is minus 13.06 volt by volt, or if we can calculate, so we have to calculate it with 20 log for dBs. So that is the value that we'll get in terms of dBs, and this is with volt per volt. Any doubts in this gain calculations? How did we calculate the gain? Is this clear to everyone? So we have got the values of R naught also earlier, right? There was a question that we solved R naught, which was, yes, this question. Here we have solved R naught also. So we can directly use the values of R naught, GM, all the values are given. RL, RA are already given. RD is known, right? In this problem, RD is not known. Yes, we have solved in the previous question, right? This problem we have solved RD. So all the values are known, so we can simply substitute them and we'll get the value as 13.06. Hope this is clear. If you have any doubts, kindly unmute yourself and ask, okay? So considering no doubts, let's move on to the next problem. So in this problem, we have to define, so let us define power gain as the ratio of power delivered to the load to the maximum available power from the source. That is Pi, which is P input is Vi square by 4 Ra, and P out is the power across load. So power across load will be, how much will be the power across the load? VRL into IRL, right? So Vi was, how much was the Vi? Source is not given. Where Vi is the small signal input amplitude, Ra is, values of Ra and RL were both given as 20 kilo ohms is the power gain. Give your answers in decibels. Okay, so let us keep it as the same Vi square by 4 Ra. VRL into IRL, let's write it as VRL square by RL. Now VRL square, we know that VRL is AV into VI whole square by RL, right? So P out by Pi is AV VI whole square by RL by Vi square by 4 Ra. This and this gets cancelled, so it is AV square into 4 Ra by RL. Given that RL and RA both are 20 kilo, so these two will be cancelled. So P out by Pi is AV square, 4 AV square. So this is 4 AV square. So how much is the 4 AV square? AV कितना था? 13.6. So 4 into 13.06 whole square. So how much is P out by Pi? What is the value of P out by Pi? And also tell me, how do you find P out by Pi in decibels?
Ma'am, it's RA and RL equal, ma'am.
Yeah, RA and RL are equal. It's mentioned in the problem.
Okay, ma'am.
What is P out by Pi? Okay, Sanjit says P
It's
out by
676.36.
6. How much? 676.
0.36.
Okay, I've got 682.25. 1 by watt. Maybe anybody else? But yeah, maybe you might not have considered 0.6. Did you consider that as well? Okay. So yeah, so main question is, so you can simply put it in the calculator and we'll get it. But my main question is that how do you find the power gain in dBs?
10 log to the base 10.
10
10
log, are you
log.
sure?
Base 10.
Okay, 10
Yes,
log
10
base
log
10,
P out upon 10. Because
P out upon Pi.
in
on
current
PI.
means voltage.
Yeah. So we have to keep this in mind, and this is very important, that power gain is always 10 log 10, but your voltage gain or
As
your
well as
current
current gain.
gain both will be 20
Both
log.
20
So
log.
anybody knows
V0
like
by
why
V in or
it is 20 log, why it is 20 log rather than
it's
10
a
log? Like,
volt square. Volt square. Because
V
power
square by
is
R
equal to
square.
volt square
because
upon
P equal to V square upon R or I square R. So this 2 that is there in the power, it comes to front, and that's why it becomes 20 log. So yeah, we can simply put this in the value, and we will get it as how much? 28.34. 28.34 dBs. So this is the value that we'll get. Clear? Any doubts? Okay, hope there are no doubts. And moving ahead with the next problem. So in this particular problem, your input. Okay, so in this particular circuit, has anything changed? Like, what are the differences that you can see? First of all, what is the configuration of this circuit? Is it CS, CD, CG? Is it CS? Okay, how many of
Current
you
source is
say
dual.
CS? Okay, let's take a poll. All of you, like, you can mention in the chat how many of you think it is CS, how many of you think it is CG, how many of you think it is CD. Hand raise mein, how would you know? Answer in the chat. Okay, so we do have got like all the options. CS, CS, CD, CD, CG, CG, CD, CG, CG, CD. Okay, so let's observe. Okay, So you have this particular circuit, right? In this particular circuit, first of all, there is a source, and the source is at source. Current source is at your source, right? There is a load resistance which is connected to your drain, right? And when we are using it as an amplifier, we consider that it is for small signal, right? So all the capacitors will be shorted and your gate is at ground. Now, when your input is from source and your output is from drain, what type of configuration is it? Yes, what type of configuration is this? With input at source and output at drain? Yes, it is CG amplifier. But everything looks very similar, right, to CS amplifier. What has changed is the location of input or the terminal from where you are supplying your input. So it is very important to look into your input supplies and where you are getting your output from. Okay, so this is a CG amplifier, it's not a CS amplifier. And also, I have told you that source node has very low impedance. So it can be used for current sources, not voltage source. So here, if you observe very carefully, the source has also changed. Like in our previous question, the source was a voltage source. This is a voltage source, right? Which is being applied to gate. Now, in this particular question, the source is a current source and it is being applied to the source terminal. Can you see the difference? So this is what I meant, when we design an amplifier, depending on our specifications and what type of amplifier we need, we define the circuits and gains and everything. It is up to us, to the designer with the specifications. Okay? Yeah. After exploring the circuit, let's move on. Here we have RA as the input source resistance of 1 kilo ohm. This is 1K. RL is 20K. What is the trans impedance? Trans resistance. That is V out by IN, where V out is the voltage and amplitudes and IN is current in ohms. Okay, earlier circuit has been modified, so it is like same 4 mega ohms, 1 mega ohm, and this is shorted. Here we have RD of 18 kilo ohms, right? 18 point something. What was the value? 18.9K. 18.9 kilo ohms. And RS. Did we find RS in any problem? Or was it given in any problem? Was RS given in any problem?
First problem.
First problem RS was given?
No, ma'am, we have derived.
Oh yeah, we derived, right? 2.77 kilo ohms. Yes, so we'll use that. RS is 2.77K. Okay, so we do know all the resistances. Now only what we need to find out is V out by IN. V out by IN. So first of all, we'll draw the small signal equivalent of this particular circuit. So here the gate has been grounded with R1, R2. Now, gate, drain, source. Source has been connected to RS, parallel RA, and a current source has been applied. Okay. Here you have GMVGS plus minus VGS. R naught R naught RD RL. This is V naught. So first of all, we'll find the value of Vs, that is this node Vs, right? So since here it is already grounded, the resistors are connected to ground. So these resistors are connected between two grounds. So there is no current flowing, there is no voltage drop. So VGS may this terminal, this particular part has V equal to 0. This is clear, right? So now with this, Vs is actually Rs parallel Ra into, so this current coming from here, GM VGS plus IN. The current coming from this source and current coming from this GM VGS will go into Rs parallel Ra. So that is Vs. Vg, as I said, is equal to 0. So your Vs is actually Rs parallel Ra into Gm minus Vs plus In, right? So the value of Vs is, let's write down, Rs parallel Ra into Gm Vs is equal to Rs parallel Ra into In. So Vs equal to Rs parallel Ra into In by 1 plus Rs parallel Ra into Gm. So this is the value of Vs. Okay. Now V out. When we want to find V out, so how to find V out? So this is this voltage. So let's simply write KCL. So when we write KCL, we can write it as V out by R naught parallel RD parallel RL plus GM VGS equal to 0. So there are two branches, right, from V out. So both the branches equal to 0. So here V out is equal to minus GM. VGS will be VG minus Vs. This is 0, so it is minus Vs. And with this minus, we will get plus Vs. So here it is GMVS, GMVS into R naught parallel RD parallel RL. Now V naught, V out is equal to GM into Vs is Rs parallel Ra into In by 1 plus Rs parallel Ra into Gm into R naught parallel RD parallel RL. So this In will come down here and you will simply get by by IN. This will give R trans. So transfer resistance you can find using this formula. So this is how you will find the transfer resistance. And the value that you'll get after solving all these is 4929.65 ohms. So was it asked in ohms or in kilo ohms? Give your answer in ohms. So yeah, we have to give our answer in ohms. And the answer is R trans is equal to 4929.65 ohms. 4929.29 0.65 ohms. So this is the answer that I've got after solving all these. So any doubts?
Ma'am, could you repeat from VS statement, ma'am?
Sorry,
Could you repeat from VS statement, VS above, ma'am?
where
Yes, ma'am.
V is?
Uh,
Yeah. What is wrong
minus
here?
GM, minus GM, VS. How did we get minus?
So see VGM VGS, right?
Yes, ma'am.
GM VG minus VS. We know
Okay.
VS is 0. So this will become minus GM VS, right?
Okay.
And this minus, and there was extra minus over here somewhere. Somewhere there was extra minus. Here there was an extra minus. So these two minus got cancelled and it became
Yes,
a
ma'am. Left hand
plus.
side there will be minus.
Yeah,
V,
so that
VG minus
minus and
VS.
this minus got cancelled and it became a plus.
Okay, okay, ma'am. And the after that equation V out by that, how did we get, ma'am? V out by R naught parallel to R D parallel to RL.
So here I have simply applied a KCL. So it is V naught by RL, V naught by
Okay.
RD, V naught by R
Okay.
naught plus GMVGS.
Yeah, got it, ma'am.
Yeah, from there. Okay. Is this clear?
Yes, ma'am.
Okay. So let's move on to the next problem. So in this problem, what is the power gain of the circuit? Give your answers in dB. RL and RA are mentioned. Let us define power gain as the ratio of power in RL to the maximum available power from the source. Okay. So in this particular circuit, somebody wants to ask something? Any doubts? Yeah, okay. So here it was asked like what is the power gain? So power gain will be P out by Pn. Pn considering that we have a current source, Pn will be In square Ra and In square Ra by 4. Ra is 1 kilo ohm. Rs was 2.77, right? Yeah. Okay. So, like in earlier case where input was voltage, the input power was Vn square by 4 Ra. So here, in place of voltage, we have changed it to current, and it is In square Ra by 4. P out will be VRL into IRL, or that is IRL square into RL, right? So IRL square into RL. Now we know that V out or V out is VRL is equal to R trans into I in, right? So in place of let's change this IRL into VRL square by RL. So in that we can simply substitute this VRL. So V out will be R
Ma'am,
trans. Yes.
how did we get by 4, ma'am? P in P in by 4.
Yeah. So earlier also here we have got the input power as VI square by 4 RA, right?
Okay, from previous question. Okay.
From previous question. So similar to that, we have simply changed the voltage to current. So it is IN square RA by 4.
Okay, ma'am. Thank you.
Yeah. So similar pattern, just current has been changed to voltage. So yeah, V out was changed. So P out will be R trans into IN whole square by RL. So gain is R trans, oh, sorry, R trans square into IN square by RL by IN square into 4 by RA. No, RA by 4. Yeah. RA by 4. Yes. Okay. So here in square cancelled. You have R trans square into 4 by RL. So the gain that we get is 4.86 watt by watt, and gain in dBs is 6.86 dBs. This is the gain that we get. If this is clear, any doubts in this particular question? Yes, any doubts? Hope the power problem is clear. Okay, so it is 8 o'clock, but still, since we started half an hour late, do you want me to extend it till 8:30 or do you want me to stop it over here? Students, hello, am I audible?
We can continue.
We can continue. So I have, I guess, 3 more questions. So maybe we can quickly go through them and then we can end the session, right? Is it okay to everyone? Yeah, okay. So in this next problem, it is given that the MOSFET has, see, here in this particular question, it says kW by L. Now here in this problem, if it is kW by L, then whether you have to consider kW by 2L VGS minus VTH whole square ID equal to, or it should be ID equal to kW by L VGS minus VTH whole square. So that is something that actually confuses. But here, since it is kW by L mentioned, so you can simply take it by 2. Okay, so here the value for ID we will consider it as kW by 2L VGS minus VTH whole square. Okay. Ah, yeah. So in this particular question, it is given that VTHP is minus 1 volt, considering that this is a PMOS. Lambda is 0, so we don't have to care about. And kW by L is zero point 0.5 milliamps per volt square. So calculate the operating points, that is Q, VSD, ISD of the transistor. So in this transistor, all the resistors are given. And what type of transistor is, what type of configuration is this? What
CS,
type of, sorry,
common source.
common source.
Common
How
drain.
many of you agree with common source? And how many of you say it is common drain?
A common drain also.
Common drain.
Common drain.
Equation common drain.
Common drain.
Common source.
So what terminal is this? The one with the arrow? Yes, what terminal is this with the arrow?
Source.
Source. So the
Source.
remaining one is drain. So if you are taking output from drain, what type of configuration is this?
Common source.
Common source. So
Common
this
source.
is common source. See, be very careful with PMOS and NMOS because it flips, right? PMOS and NMOS made the terminals just flip. So they might sometimes confuse. So that's why be very careful with the terminals. Just note down the terminals, whatever you see. Where is the arrow? Always the arrow represents source, and in BJT it represents emitter. So keep that in mind. And with that, we can go ahead. Okay, so always, first of all, first thing you need to see is whether your transistor is a PMOS or NMOS. And then you have to find out your terminals. Depending on your terminals, you will then solve the equations. Okay, so
Can we
yeah,
explain in
this is
such
a,
way, ma'am? Input,
sorry.
input is voltage, no, ma'am. Can we say in such way to CS?
Uh, See, sometimes that might be tricky because there is a possibility that you have a CG amplifier, but somebody has designed a circuit and said that is going to apply voltage at source. That is possible. So depending on input, if you judge that okay, the input is voltage or input is current, then you might go wrong. So better we how to judge is by identifying the terminals. That is the best way, the most easiest, and you will never go wrong with that.
Okay,
Just
ma'am.
find out the terminals and see which terminal has input and which terminal has output. So whatever terminal has input and output, so depending on that, the third terminal is common. So that is the
Okay.
common, that configuration.
Okay,
So
ma'am.
here it is common source, since source does not have any input or any output. As simple as that.
Okay.
Yeah. So in this particular question, first of all, you have 8 volts of VDD, 20 kilo ohms of your gate resistances. And yeah, operating point always means DC operating point. We also call it biasing point. Okay. So whenever there is a operating point, it is always a DC that we are talking about. And we also call it biasing or biasing point. So it is DC. So when it is DC, what will happen? Your capacitor will be open circuited, right? So this resistor will not come into picture. What is the voltage that we'll see over here with 20 kilo ohms? We'll see 4 volts at the gate, right? So we see 4 volts at the gate, source is at 8 volts. Now ID for for PMOS is kW by 2L VSG minus VTHP whole square, right? So this is how much? Zero point 0.5 milliamps per volt square into by 2 into VSG 8 minus 4 minus what was VTH? 1. 1 ka square. So it is 8 minus 4 minus 1. 3 square. 0.5 by 2 into 9 milliamperes per volt square. 4.5 by 2. 2.25 milliamps. So ID is 2.25 milliamps. We've got ID, right? So first of all, 2.25 milliamps, we only have one option with 2.25. So we can simply go ahead and take the option D. But just to be sure, let's also solve for VSD here. VSD, right? So how do we get VSD or VD? How do we write VD? It is VS, or let's say if it is VSD, that is VS minus VD. So VD is VS minus VSD. And actually VD is also IDRD. So we can write it like VSD is equal to VS, which is VDD, minus ID into RD, that is 8 into 2, oh sorry, 8 minus 2.25 milliamps into 2 kilo. So which is VSD is 8 minus 4.5. So VSD is 3.5 volts. See, we have got the final answer, right? So sometimes what happens in when you have options and you have to select out of many, and there are many things to solve. So most of the times, if there is no trick played with the options, there is only one single option which is correct. So here, as we first solved, like for ID being 2.25, we could have directly gone and ticked D option, which was the correct option. But just to be sure, we solved the other one also. Because sometimes there might be a trick in the option. Let's say there are two options with current 2.25, but VSD is 3.5 and 3.75. Then you have to obviously go and solve. But sometimes if there is no trick played, it is straightforward. So you don't have to waste your time in the exam, and just with solving, like getting one correct answer, you can go ahead and select your option. So that is also possible. So any doubts in that question? That was an easy question, right? Hope everybody got that right, got that answer. Just in case if you have any doubts, please let me know.
Excuse me, ma'am.
Yes, go ahead. And what is the problem in this particular question?
Found the operating point, which means that the transistor can operate in this point. For practically,
Wait, I could not get, you were disconnected in the beginning. Can you start from the beginning? Yeah.
ma'am, am I audible?
Yeah, you are audible. You were disconnected earlier. Yeah.
Okay, okay. Ma'am, in this problem, we have found the biasing point of a transistor,
Yes.
MOSFET, which means that the MOSFET can operate in these points. Practically speaking, while working with the MOSFET,
Hmm.
we need to find a biasing point for all of the transistor we are working with, ma'am?
See, first things first, biasing point is to set your transistor to your desired region of operation. Say you want to operate your transistor in linear region. So you will fix your biasing such that your transistor operates in linear region. If you want to use your transistor in saturation region, you will bias your transistors such that your transistor is in saturation region. Now, let's say your transistor is in saturation region now. Then for amplifier, for very specific amplifier, I'm talking about. Uh, I'm saying that let's say there is an amplifier, and you know that for amplifier you'll need saturation condition, right? So first of all, what you do is you take your transistor, you put your transistor into saturation using resistors, biasing, everything. Once your transistor is in saturation, then you apply your AC signal for it to amplify. So when you are actually amplifying your signal, in that condition, you will have AC and DC signals both, where DC is used to keep your transistor in saturation and AC is used as input so that you can get an amplified output. So in an amplifier operation, you will always have both AC and DC working together. While analyzing, theoretically, why we put while AC condition, while studying the AC condition, we put DCs to ground, and while considering DC condition, we put ACs to ground, is to simplify the calculations. But in reality, both of them work together. Like both the signals AC and DC are provided to your circuit and they work simultaneously. But it's just that the theoretical analysis of both the signals together is very difficult. So that's why we go for considering one particular signal and solve the equations. Otherwise, in real life, you will have both of them, AC and DC. Is this clear?
Yes, ma'am. First,
So
we need to verify whether our MOSFET is in on or off condition, and then we
yes,
have to make it in saturation, and then we have to bias. Am I
yes.
correct,
So
ma'am?
no.
Okay.
So first of all, you will. So when you say your transistor is in on or off condition, what does that mean? That means your transistor is in saturation, linear, or cutoff region, right? And when we say that whether your transistor is in saturation, linear, or cutoff region, how does that come out of? Like, where do that come out of? Is basically from your biasing or from DC operating point, like where you fix your transistor. Whether you have fixed it in cutoff region, saturation region, or your linear region. Depending on that, your transistor turns on and works in that particular region. Over that, what you do is you apply your AC signal. And when you apply your AC signal, you will get your output. So that is the idea. You'll get your amplified output.
Yes, ma'am. Thank you.
Yeah.
Ma'am, how did we get 4 volt as VGS 4 volt, ma'am?
VGS 4 volt. Voltage divider.
What about voltage drop at 10 kilo, ma'am?
No, 10 kilo ohm is not coming into picture. No, see, we said we are considering DC operating point. We are only considering DC. See, there are
Okay,
two things.
AC is grounded,
Wait,
ma'am.
wait, wait. First of all, first thing, there are two things that you have to keep in mind. In practicality, when you are working in your labs or in your circuits, say using your simulators and everywhere, you will have both AC as well as DC sources working simultaneously, practically, in all your circuits, in labs, as well as in simulations. But while solving your theoretical problems, we consider one type of source at a time. So we either consider the DC source or we consider the AC to simplify our simulations or to simplify our calculations. So when it is said that you have to find the operating point, so operating point basically means the DC points, so the DC voltages and current. So for that you have to perform DC analysis. For DC analysis, you will put your AC sources to short or ground and you will only use your DC sources. Now, let's say when it is asked, what is the signal output, what is the amplification, what is the gain, that is for AC signal that you give at the input. At that time, you have to put your DC sources to AC ground. They are not ground, they are just AC ground to simplify your calculations, and you will find the output signal corresponding to your input AC. There you will not consider any DC. Am I clear?
Yes, ma'am.
Any doubts to anyone? See, this is very important to keep in mind, because when we are solving the problems, we take many assumptions and solve just to get ourselves to get rid of those complex calculations that will come into picture. But in reality, those things don't work the way that we assume. So it is very necessary to keep in mind the difference between both, how practically your circuit should look like and how it works, and how you solve them theoretically. So these two things are two different things, and you have to keep them in mind separately. Just don't get confused and mix them up. Anybody has any doubts, you can come again, ask
Ma'am, I
number
have
of
a
times. Sorry?
Ma'am, I have a doubt.
Yeah,
Ma'am,
please.
when we calculate VG, the operating point,
Yes.
we consider the voltage applied across VDD, that is DC point, right?
Yes.
So when we write a small signal circuit for it, the
Huh.
VDD we are going to make it 0.
Yes.
So VG, which is a function of VDD, will also be 0, right?
Why? At that
Ma'am,
time, you will have your V in, right?
but VG is due to only VDD, right?
No, who
Because
said?
that's how we
See,
calculate
no,
VG, right?
no,
The
no.
voltage divider method.
Wait, wait. The VG that I am talking about is DC operating point. The VG that you are talking about in small signal model is due to V in. So that V in will also drop across your two resistors of 20 kilo ohm and 20 kilo ohm, and they will come in parallel to one another, and your circuit changes. But there the source is different. There you will calculate, you will perform all your calculations with respect to your V in. But in DC you will calculate all your calculations corresponding to VDD. So that is what I am telling. Like when you have to go for a AC analysis or small signal analysis, you will only consider the AC source, that is V in, or your signal. When you have to find your DC operating point or biasing point or operating point, you will go for DC analysis. There you will consider your VDD. Then you will not consider your V in. Am I clear?
Yes, ma'am.
Yeah.
So during small signal analysis, VG is a resultant of V in.
Yes.
Okay.
Yes. Any other doubts? Okay, maybe we can stop over here because it's already going to be 8:30 now. We can stop with this particular question, and we can take up the next questions and coming next week. So we'll go on these circuits of CS, CG, CD for I guess 1 or 2 more weeks now.
Excuse me, ma'am.
Yes.
Just a general question I wanted to know. Is there problem solving session tomorrow also being conducted?
Yes.
So actually, in that particular course, NPTEL area, so
Yeah.
there I could find only yours one, this particular session which is recorded. I don't see the other session being recorded because I can attend only one day, either Monday or Tuesday.
Yeah. Yeah.
So,
No,
so
you
is it
can find it
repeated?
like that shared the sheet you see, right? The Excel sheet where
Uh-huh.
I mentioned my YouTube link as well as my these notes, the drive link for this notes. So
Yeah, yeah,
in
I
that
can
same
see your
particular,
link.
yeah. So
Huh.
in that particular sheet,
Mhm.
downside you will see another table. So the top table is
Okay,
mine, and the bottom
okay,
table
okay,
is with another TA.
okay, okay,
Yeah.
sure, sure. I will just double check.
Yes, yes. You can double check. So the first table is mine, and the
Hmm.
next table is from the other TAs. We do have our details also mentioned, so you
Okay.
won't get confused. But yeah, it is shared. You can double
Okay.
check it. Yeah, he is
Okay.
also uploading it on YouTube. So we do have to upload it on YouTube. So you can find his lectures as well.
Okay. Okay. Thank you.
Yeah. Thank you. Okay. Any other doubts?
The doubt in the first problem. Uh,
First problem.
yeah.
Okay. Yeah, this is the first problem, right? Huh. What is the
Uh,
problem?
can we approximate the value of RD? Like if we take the value across the V naught,
Can we
if we
approximate the value of ID?
RD,
RD.
RD,
But
because
why do you want to approximate it? See,
uh,
rather than going for taking some value of RD, approximating it, how do we avoid the method where we don't have to use RD? That is the better one, right? Rather taking a wrong value and solving it. Don't you think so?
if I keep my MOSFET at the edge of saturation, like we know that if my drain current goes beyond uh, zero point 0.5 volts, the MOSFET would be in saturation. So if I
No, that
keep it,
I understand, but how would you know that your transistor is just at the edge of saturation, not into deep saturation? How can you make sure that?
oh yeah, yes,
No, right? So rather than assuming and like assuming something wrong, how about avoiding it and not taking that path? That would be much better, right? Don't you
yes,
think
yes,
so?
yes.
Yeah. So that's why, because it's always better to avoid something which is not known rather than assuming something which might lead to a wrong result. So that is what uh, I basically meant. Yeah. Because there is more certainty in this particular method, right? We are not assuming something like there was one method, one problem that we did of diode in first week, remember? There we assumed that diode was on looking at the voltages, but actually the diode was off. That came out from the calculations. So sometimes there is a possibility that the assumptions that we have made might go wrong. So we can avoid the assumptions if we can, right? So yeah, that is the idea. Anything else?
Ma'am, where can we get this recording link, ma'am?
You can get it on YouTube. So what you people can do, you can subscribe to my channel and there is this bell icon thing, right? So you can go for that. You can tap on the bell icon. So the moment it gets uploaded, you will see it on your YouTube. Or otherwise you do get this shared sheet, right? Like you see that Excel sheet where you can get all the links as well as these hard copy like these notes in soft copy which I'm preparing. It is an Excel sheet, or otherwise if you like subscribe to my channel, so and with that bell icon, I guess it gives you the notification that a new video has been uploaded. So through that, the moment it gets uploaded, you will get the notification in your YouTube. So you can go either way.
Okay, ma'am. Thank you.
Yeah. So if there are no further questions, maybe we can disconnect from here and join next week. See you all next week. Hope you have a wonderful evening ahead. Good night, everyone. Bye. And yeah, happy Independence Day, all of you, for tomorrow.
Same to you, ma'am.
Okay.
Thank you. Same to you.
Thank you, Anand.
Thank you. Thank you for joining.
Thank you.
See you all next week. Bye, everyone.